So yeah, so first things first. So let me introduce myself. I'm Ritojit. I'm a PhD student at IIT Kanpur. So I am one of the TAs in this Advanced Condensed Matter Physics course, and this is one of the weekly interactive sessions that we're having, and another one is on Monday. So I've got some problems that I would like to discuss, and so Sanjeev, I think some noise is coming from your side. Can you for now mute yourself? Okay. So the
Hello. Hello.
yeah, Sanjeev.
Yes, sir.
Yeah. So a lot of noise is actually coming from your
Yes, sir.
side.
Due to poor network, sir,
Ah, okay.
some problem arise.
Okay, okay. Okay. So anyway, so I have got some problems that I'd like to discuss today, which is mostly from the week 2 or week two's content in this Advanced Condensed Matter Physics course. And so let me just share my screen and start this session. Yeah. All right. So this is mostly about week two's contents. So there are the things that I would like to discuss today is some tight binding models. So you all can see my screen, right? Okay. So I'll firstly I'll discuss some tight binding models so that you get a practice of how to do calculations with them. And then I'll be talking about some Feynman diagrams. So how do you actually do it, and in a not very formal level. So we'll try to do some problems with Green's functions, and then we'll actually look into some simple cases of Hubbard model. So which is, for example, is single site Hubbard model and two site Hubbard model. So yeah, so let's begin then. So it will be helpful if you also keep a pen and paper handy so that you can also work out along with me. So at certain points I'll just pause so that you can do some steps. Okay. So firstly so tight binding models. So and the problem that I've chosen in such a way that it actually will help you to solve the week three's assignment, which is some Feynman diagrams. So yeah. So first of all, let's actually look into some 1D tight binding models. So in 1D, let's say I have a chain of atoms like this, and so these are all atoms, and then let's say this is I and this is I plus one site. Okay, and let's say there is a hopping between these two sites. So which is given by minus t. So for this I can write the Hamiltonian, which is given by something like this. Okay, and so now if if my these two ends, let's say this is my first site and this is my nth site, if this is these are not connected, then we call it open boundary condition. If 1 and n are not connected, and otherwise if 1 and n are connected, then it is then we will call it so it has a periodic boundary, or we will say that it has a periodic boundary condition. All right. So normally what we'd like to do is whenever we are given a Hamiltonian, we'd like to find its eigenstates. Okay. So now there are so multiple ways of doing it. So we can actually write the Hamiltonian, let's say in a basis where it is like a matrix. So in the real space, it is like a matrix which has 0 sitting in the diagonal, and only off diagonal has some minus t elements, and so on and so forth, and everything else is actually 0. So but this matrix can be quite large, right? So it is actually n cross n if you have n number of sites. So so I mean, it is hopeless to solving the eigenvalues for this. So then you can put this to a computer, right, and it can find you the eigenvalues of this system. But there is one another simpler way, which is fully analytical. So where we'll use the periodic boundary condition. So now if we have this periodic boundary condition such that 1 and this site 1 and n there is a connection. If we were talking about periodic boundary condition, then actually momentum or let's say block momentum is a good quantum number. Okay, so we can actually write the Hamiltonian so that we can exploit that good quantum number nature of block momentum. So to do that, so let me define some transformations. So Cj is actually the annihilation operator of at jth site. Okay, so and so these are just fermionic operators, and they anti-commute and all. And so I am not assuming any spin right now. So right now these are actually spinless. Okay, so what do you mean by spinless fermions? So I mean, that is something that so people use, but let's say these are spinless. So later on I'll show you why these are called spinless fermions. So let's say these are spinless fermions, and I can actually express them in terms of something like this. So this is something like a Fourier transform, a discrete Fourier transform. Okay, so this k are actually so k belong to first Brillouin zone. So in 1D the Brillouin zone is actually just minus pi by a to pi by a, and so a, where a is a lattice constant, so here I have already taken a to be 1. Okay, so that you can always take, so just for some convenience. And then what I will have to do is I have to plug this Fourier transform, discrete Fourier transform, into this Hamiltonian. Okay, I'll have to do this substitution. All right, and there is summation over k. Yeah, so let's just write the Hamiltonian in terms of this this ck dagger and ck. So I'll just plug these things in one by one. So let's say the first thing is given by 1 by square root n, and let's say k1 to the power minus I k j and c k1. So this is I'm substituting for first this part. So because see there is a dagger, so I am just flipping the sign of this. I mean I'm writing it as a minus ik, and the ck is all, there is also a dagger appearing there. Okay, and the second term is can be written like this. there's no dagger here. So okay, so let's arrange all of the terms. So at any point, if you have any question, just feel free to unmute yourself and ask. Okay, so these are just a recap of whatever you have learned. So okay, so I can actually do some more manipulations. So here I can actually use one of the identity. Okay, I have missed a JSON. So I can use one of the identity. So the identity is something like this: sum over j 1 by n is given by, it is a Kronecker delta k2 k1. Okay, so this is I mean, you can verify this, which is simple to verify. So now after using that identity, I'll be left with right. And then, as you know, the Kronecker delta has the property that, so if I write delta ij, so it is only 1 if I is equal to if I is equal to j, or this is 0. Okay, so now I mean, using that fact, I can actually sum over let's say k2. So then my this Hamiltonian becomes something like this: I k1 dagger c k2. And there is obviously one Hermitian conjugate part, which I have I've forgotten to write, but just remember there is a Hermitian conjugate part. And okay, so now I can take the Hermitian conjugate and the term itself. So and I can write it like k1 e to the power minus I k2 and c k1 dagger c k yeah, just k1. And then you just use the identity of cosine. This is nothing but a cosine. Dagger c k. So this is the Hamiltonian. Okay, and Hamiltonian has eigenvalues. So like this is a diagonal Hamiltonian, right? So at each of the k point, it has the eigenvalue. I can just write it like this: ek is minus twice of t times cosine of k. Okay, and you have already seen this dispersion. So this is called dispersion relation when you write E versus k. So you already seen this. So the first below zone goes from minus pi to pi, which I have already mentioned, and then just this is a cosine, right? So something like this. Okay, so this is your zero energy, and I mean, this is your epsilon k. So this is all clear, right? So any doubt in this, derivation? So what I have done is I have just started from a real space Hamiltonian, or lattice Hamiltonian, or tight binding Hamiltonian. Then I have actually used a periodic boundary condition so that I can write the Hamiltonian in the basis of the CKs. Okay, CK is the annihilation operator of a block momentum k. So when I do that, I just plug in this relation in the Hamiltonian, which was in real space. Then after doing some simplification, I obtain a diagonal Hamiltonian, right, which was not there if we just look at the real space Hamiltonian. So real space Hamiltonian is a large matrix for which we cannot actually find the eigenvalues, but we, as soon as we include periodic boundary condition and go to momentum space, everything becomes very simple. So I mean, so this might look very simple to you, but actually this case is very, you can generalize this to higher dimensions, right? So for example, so here I have shown you what happens for a 1D lattice. Now you can ask, okay, what happens for a square lattice which is in 2D, okay, and what happens for cubic lattice or higher dimensional lattice and all. So the answer to that is, you can derive it yourself, but the answer is actually the Hamiltonian will be just the similar thing. So KDI, so let me write it like this. So D KD cosine of KD C KD dagger C KD. So where the D is a dimension of the lattice. And you, I mean, just realize, I mean, if you can understand that, I mean, it just tells you that this whole thing is kind of very much generalizable, and you can go to d-dimensional space and find the dispersion relation if you have something cubic or hypercubic lattice, right? So yeah, so this is something that I just wanted to point out. So any question? So any question at any point, if you have, just feel free, right? Okay, so now if we have something something like this, which is very simple, we have just a single band, and you can find okay, you can actually make the problem harder. Okay, for example, we started with a chain which has only one only one sublattice, right? So in the unit cell it has only one sublattice. Okay, so from that, so you can actually see that we have only one of the band. Okay, so in solid state physics, or whenever we will do the tight binding calculation, this is, I mean, this is something that you will always find is, so number of let's say number of atoms, or let's say number of sublattice in unit cell is equal to number of bands. Okay, so this will be always the case. Okay, so there are some arguments why this is the case, but I mean, let me not go into that, which is fairly simple. I mean, if we can also try to think why this is the case. Okay, so let me actually focus on a little bit non-trivial model. So this is still kind of very much trivial. Okay, we have already done this in the course, but so let me actually do something a bit more non-trivial. Okay, so I have, let's say, some chain, and here I have not a single atom in the unit cell, but I have two atoms in the unit cell. So here the orange, so let's say this is atom B, and this pink is atom A. Okay, so you can see that now to define the unit cell you have to take both of them. Okay, so I mean that's how you can only describe a lattice, right? So this is a Bravais lattice with a this kind of AB motif, if you like. So yeah, so now I mean, the hoppings can be somewhat non-trivial, right? So a electron from here can hop to here. Okay, so which is something like the electron is hopping within the unit cell, so you can call it is a intra-cell hopping. Okay, and the electron can also hop between the two unit cells. Okay, so which you can call inter-cell hopping. So let me actually give some symbol to this. So let's say this hopping we will call it as some u, let's say v, and this hopping we will call it w, call as w. Okay, and this is ith unit cell, and this is I plus 1th unit cell. Okay, so just from this information, nothing else, we'd like to construct the tight binding Hamiltonian, and we like to do the similar things, like we would like to go to momentum space, and we like to find what are the bands, what are the energies, right? So now let me actually first try to write the Hamiltonian. Okay, so you just follow along that how I'm trying to do it. So because this is, I mean, if you are trying to do something in condensed matter physics, this should be your bread and butter. So so let me actually first try to write this v hopping, right? So which is given by something like summation over I, and so here I have two flavors of fermions, let's say A and B. So Ca or Ci A dagger Cib, so with amplitude V. Okay, so just look at this quantity. I mean, this looks very simple, but this tells me that so one electron has been annihilated at B and is created at A. So that diagram actually looks something like this. So I am starting from B and I am hopping to A. So this is what the operator means. Okay, so if you, I mean, actually second quantized Hamiltonian is kind of very I mean, it is to visualize all of the processes that can happen in a Hamiltonian. Okay, it is a list of all of the processes that can happen. So where the electron can go and whatever the electron can happen. So the Hamiltonian has everything, the list of everything, right? So this is just this part. Now I am still left with this other hopping, right? So for the other hopping, we can see that this is actually happening between two cells, I and I plus 1. Okay, so I'll have to make sure that I involve both I and I plus 1. So let me actually write this part. So now what I am doing is I am trying to annihilate one particle from ith unit cells, B sublattice. So I write Cib, and I am to create the electron at the 8th site of I plus 1th cell. Okay, so because I like to create it, so I'll give it a dagger, and then you just give it the amplitude W. Okay, so this is actually I mean, this is not a toy model, I mean, so to speak, but this is actually something which is seen in a polyacetylene chain. So polyacetylene chain has some kind of structure like this, and so there are some double bonds sitting somewhere, and which you can model like this. So this is the simplest model of a polyacetylene, but this has some nice features. Okay, so this is the very simplest kind of topological insulator that you can have in one dimension. Okay, so we'll be not talking about what is the topology in this model, but what we'd like to do is so we'll just try to get the dispersion, right, band dispersion of this thing. So so this is not all. We obviously have Hermitian conjugate part just to ensure the hermiticity of the Hamiltonian, right? Otherwise we will not get real eigenvalues. So yeah, so now again in real space, if you like to write the Hamiltonian, you will see that this is actually quite a large Hamiltonian, right? So now if you have n number of sites, then it n number of unit cell, then it is a just 2n times 2n dimensional matrix. Okay, so where you will have 0 sitting on the diagonal, so V is sitting somewhere and W sitting somewhere. Okay, so it is a tridiagonal matrix. Okay, tridiagonal means only 3 diagonal components are non-zero, but here actually the diagonal is also 0. Okay, and so on and so forth. But I mean, you can see that this is actually hopeless. You cannot solve it, and analytically you have to just plug this thing in the computer, and that will generate some solutions for you, right? So so again we'll like to use a periodic boundary condition. Okay, in periodic boundary condition this will become really simple, as we'll see. So now because I have these two flavors of electrons, so electron on site A or site B, so so Sanjeev, can you mute yourself because a lot of noise is coming from your side. Yeah, so I have actually muted Sanjeev. Yeah, so actually a lot of noise is coming from your side. Okay, so let's continue. So I mean, is this okay? Is everyone with me? So are you getting something like what I'm trying to do? At any point, if you have any question, just please feel free to ask. All right. So okay. So so let me define a Fourier transform, discrete Fourier transform for this case also. So we'll assume that this is a periodic boundary condition. Okay. And let me define the Fourier transforms. Okay, so I'll define the Fourier transform in a similar way, but because now I have two of these flavors, A and B, so I'll have to define two Fourier transforms for both of these. So let me write this properly. So Cj A is given by 1 by square root n ik dot ik j, and then C k A. Similarly for B as well, we'll do the same thing. E to the power I k j C k B. So these are all fermionic operators. They anti-commute. Okay, you can generate all of the anti-commutations. And if you just take the dagger, if you just take the conjugate transpose or just the dagger of these relations, you can also define what is the Fourier transform of the daggers of the creation operators. E to the power minus I k times j C k a dagger C j B dagger is given by 1 by square root n k, and e to the power I k j k dagger B, yeah, something like that. Okay. All right. So now so what we'd like to do is we'll take these transformations and we'll just plug this thing into the Hamiltonian. Okay, so now let's just do that. You can also follow along. So the first term is 1 by square root n k to the power I k1 j c k a dagger times 1 by square root n k2 e to the power I k2 j c k b. Okay, so so this is the first term, and then I am left with another term which will be similar, and then it becomes 1 by square root n k1 e to the power actually minus I plus okay, minus I k1 times j plus 1 c k k1 a dagger. I'm missing some indices here. Okay, and then the another term which is given by k2 e to the power I k2 and j c k2 b, right? So this is I have put everything together, right? So now let's just simplify things. So the Hamiltonian will become something like this: v by n summation over k1 k2 and summation over also j, and I'll just directly write this exponent together: k2 minus k1 j c k1 dagger a c k2b, right? So this is the first term, and then similarly the second term is given by w by n k1 k2 summation over j e to the power I k2 minus k1 j e to the power minus I k1 j, and then c k1 a dagger and c k2 b, right? So now I have everything. Okay, so now similarly I'll use the identity, the same identity that I have used last time as well. So if I have something like this, 1 by n summation over j k2 minus k1 j, so then this is just Kronecker delta k2 k1. Okay, so if you'll just use that in both of these cases, I mean for both of the terms, then you will end up with something like this. So 1 by n will be absorbed, then k1 k2 delta k1 k2 c k1 dagger a c k2b. Okay, and similarly the other term is given by w k1 k2 and similarly 1 by n factor is also gone in the definition of Kronecker delta, and then I am left with e to the power minus I k1 j and c k1 a dagger c k2b, with delta k1 k2. Okay, so you can sum over k1 or k2 whatever, and just I am writing it directly, ck dagger a ckb plus w kc k dagger a ckb with this another exponential factor minus ik1 ik, that's it. So it will be minus ik. Okay, so now I mean you can write this thing in a basis, so something like, so let me actually write this thing as hk first. Okay, so h is given by some block Hamiltonian, some of these block Hamiltons on all over the momentum. So hk is given by v ckA dagger ckb plus w ckA dagger ckb times e to the power minus ik, right? So now you can see that you can actually write this in a very simple form, something like this. So you can write this in a matrix form, okay, and try to find the eigenvalues. Okay, and there is also Hermitian conjugate, I must not forget that, c k b dagger, and then I'll have the ckA and ckb. Okay, and in between I'll just put in coefficients, okay, just to get back the Hamiltonian. So you can see that this Hamiltonian is actually a bilinear in this ck ckb, and you can always write this in a matrix form like this. Okay, so now let me fill up those coefficients in the matrix. So you can see that there is no term like ckA ka dagger, okay, or ckb kb dagger. So only there is a and b. Okay, actually so that's why you can directly put in the diagonal 0. Okay, 0 sitting in the diagonal, very simple. And you can see that between the connection, so I mean it is helpful if you just put some AB and AB notations here as well, and just to do this calculation. So you can see that between A and B there is actually coupling sitting like this. So this is the whole coupling sitting at within A and B. So you just go ahead and write that with V plus W e to the power minus ik, and also here V plus W e to the power ik, right, because Hermitian conjugate, so I have to just write take the conjugate, so k ik becomes minus ik, something like that. Okay, so the Hamiltonian matrix, so let me write it as M, is given by just 0 V plus W e to the power minus ik, V plus W e to the power ik. So now you see that we actually started with a real space Hamiltonian, which was 2n times 2n, which has 2n times 2n dimension, but using periodic boundary conditions we have actually reduced the whole huge Hamiltonian into this smaller 2×2 Hamiltonian. Okay, so I mean this is actually we are doing a basis transformation, we are going from a real space Hamiltonian to a momentum space Hamiltonian, and this is just a unitary transformation. So whatever transformation I have introduced here, so all these things are actually unitary transformation, you can check that. Okay, so with this unitary transformation, I know that when I do unitary transformations from my quantum mechanics, that doesn't change the eigenvalues, right? So this will exactly reproduce the same eigenvalues, I mean of that really large Hamiltonian, okay, if I have periodic boundary condition. So okay, so now let's go ahead and try to calculate the eigenvalues or bands of this Hamiltonian. So for any 2 cross 2 matrix, you know that I can always try to write it in terms of Pauli matrices. That actually makes my life a little easier, so that I can find the eigenvalues, okay. Because Pauli matrices eigenvalues are simple to calculate. So for example, if you have something like this, A sigma x plus B sigma y plus C sigma z, so then the eigenvalues are actually given by plus minus square root A square plus B square plus C square, okay. So we just use that technology to kind of find the eigenvalues. So let me write it in terms of that Pauli matrices. So let me expand out the e to the power I k's, okay. So then this becomes W cos k minus W I W sin k, and then I will have V plus W cos k plus I W sin k, okay. So you can actually write this in terms of something like this. So you have real part, I mean one of the Hamiltonian has real part, or let me actually do it in an even more simpler way, P plus W cosine of k, okay, times sigma x, okay. So I have just taken this and this, and I have written this in terms of a sigma x Pauli x matrix, and then for the rest of the term I'll just take W sin k common, and I'll be left with just sigma y, right? So now we see that there is no sigma z term, okay. So if that is the case, then the eigenvalue is actually quite simple. You can find out the dispersion epsilon k, let's say plus minus, because these are two bands, is given by something like this, plus minus square root V plus W cosine of k whole square plus W sin k whole square. So you can simplify that, V square plus 2V W cosine of k plus W square cosine k square plus W square sin k square. So you see from this, cosine square and sine square k, they will actually give you 1, and you will be left with W square from this term, and I have a square root. So V square plus W square plus 2VW cosine of k, okay. So this is your dispersion, okay. So now this might look a little bit complicated, but we can plot it, right? We have some computer, we can actually plot it. But let me actually show you how does the plot looks like. So this is I mean this is somewhat complicated than what we have already seen for particle on a chain, I mean one sublattice things. So here the dispersion will look something like this. So let me actually first draw it. So my Brillouin zone is from minus pi to pi, okay, because I am in 1D, and then the dispersion actually looks something like this. So let me try to not mess up the drawing. So something like that, okay. So this is your ek plus, and this is your ek minus. So and you can find out what are the values of these things. So this is your k axis, right? So this is your k axis, and at k is equal to 0, you can see that this actually becomes 1, and you are just left with V plus W whole square root. So then you can see that this will be nothing but V plus W, okay. You can put a mod if you're not sure whether they're positive or negative, and this is V plus W mod, okay. So these are the maximas of the bands at k is equal to 0, and then we see that there are some minimas at pi and minus pi. So what is the gap that we're talking about? So the gap, so you can also find the expression of the gap if you put if you put this k0 k pi in this expression, k pi in the dispersion. So k at pi will give you -1. So then you will be left with v. So this point is actually v minus w mod, and this is also given by v minus w mod, but with the minus. So the band gap, which is actually very important to describe many qualitative physics. So the band gap is actually given by twice of v minus w. Okay, so there are two important energy scales that one looks when one has a band structure. So which is the bandwidth? So how thick is the band? So for what does that mean? So that means that the band goes from which energy to which energy. For example, here the band actually goes from this energy to this energy. Okay, so this is actually the band gap, the bandwidth. Okay, and the band gap is what is the gap between the valence and conduction band. That is your band gap. Okay, so here the bandwidth is given by v plus w and minus v minus w. Okay, so this is your bandwidth. So yeah, I mean, this is typically how you actually calculate this kind of band structures. But so this model has actually I mean, it is a very famous model. This is called the SSH model, which is, as I mentioned, this is actually a toy model for a polyacetylene chain. Okay, so now I have told you that what happens when it is on a it is on a circle. I mean, the edges are connected, 1 and n are actually connected in this model. But there are actually many interesting things that appear on the boundary also if you do not connect them. Okay, so as I mentioned that these are simplest example of a topological insulator. So what property it has is so it actually has, so if you plot the if you just put the whole real space Hamiltonian in a computer and find the eigenvalues and eigenvectors, which you can do very easily. There are many linear algebra packages in Mathematica, Python, MATLAB, whatever you use, in C++, whatever you use. So you can plug in the whole matrix into your computational system, and you can find the eigenvalues and also the eigenvectors, right? So you will see that for some regions, like when v is greater than w, then you will see that you will get exactly energy is equal to 0 eigenstates, okay, as your eigenvalues. And you will see that interestingly those states will be localized at the boundaries. So this is I am trying to draw the 8 states. Okay, so these 8 states are actually localized on the boundaries, and you can so I mean they actually don't talk to each other, so they decay very fast. Okay, at the two edges, I mean they are there at the two edges, but they decay very fast in the bulk. Okay, but so there are some finite energy states also, so which is E greater than 0 or E less than 0, finite energy states also, which doesn't have this feature, which are actually kind of extended. So they will be something like this. Okay, they are extended states, but E0 states, these are actually localized. Okay, and these are localized, and these are protected by something called some symmetries. Okay, so these are protected by time reversible symmetry, particle hole symmetry, and chiral hole symmetry. Okay, so there are some symmetries which is protecting these things. So as long as these symmetries are there, so you add any perturbation to the Hamiltonian, you add disorder, you add any external perturbation to the Hamiltonian, these edge states will not go away. Okay, these edge states are really robust. Okay, so on the other limit, if you take v is less than w, you will see that there is no zero energy states, and there is no edge states like that. Okay, so these are actually two topological distinct phases, okay, which actually characterize this edge state. Okay, so probably we'll learn some concepts about topological insulators as the course proceeds, but for now we'll just stop at here, because we want to look into some other things. So any question until now? So any question, if you have any question, please feel free to ask. Okay, so So are you following any of this? So let me ask. So Payal Bhattacharya, are you following any of this? Any question do you have? Or
No,
Sonjeev?
it's clear.
Yeah, okay. So and Sanjeev, is this okay? Okay. So anyway, so let's actually continue. So you see that uh, so we see that so the way of calculating the dispersion is kind of very you have to do a lot of things, like you have to do Fourier transformations, you have to use some identities, right? So it is not very I mean you can I mean it is, let's say this is very much error prone. Okay, you can make a lot of mistakes because you have to substitute a lot of things, you have to keep track of a lot of terms. So there is actually another very interesting way, a very simple way to find the dispersion, okay, which is you can generalize to any dimensional Hamiltonian 1D 2D. So just by eyeballing, just by looking at the system, you can directly write the Hamiltonian. Okay, so let me just try to show you the trick. How do you do that? Because that actually comes handy. Let's say you are trying to check whether your calculations is right or not. So you can do this thing by properly doing all of the steps, and or you can actually directly eyeball what the dispersion will look like, what the Hamiltonian look like. Okay, so that is useful in many cases. And so let's just look at this Hamiltonian only. Okay, so this SSH Hamiltonian. So we will just take this, and we will also generalize this. We will also show how do we generalize for higher dimensional lattice, for graphene, something like graphene, or something even more complicated. Okay, so let's just try to see how do you do that. So okay, so let me actually first start with again the 1D. So in 1D I have some this single unit cells, I mean single atoms in the unit cells. So there is hopping happening between these two nearby atoms. So this is I plus 1. So normally your first thing is to first isolate what is the repeating element in the whole chain. Okay, so here I can see that the repeating part is just this one. Okay, only a single atom actually repeats itself. So so now what you do is you actually so the Hamiltonian is given by something like this. You actually write this T hopping. Okay, and whenever you hop, in which direction you hop. So let's say this has only one lattice, lattice or primitive vector. Okay, so you just take that hopping element T, and you just pair this up with the e to the power I k dot a. So here it is 1D, so I'll just write ka. Okay, so electron hops from here. So for that I'll just write a T, and because these sites are separated, so I'll just write e to the power I k a. Okay, so if I have some other things like other directions, other primitive vectors, so I'll just write ek dot some ai. Okay, sum over I, something like that, and ti, but I'll come to that later. First let's understand the simplest thing. So I have so this is for this kind of hopping, but I have also the Hermitian conjugate process. Okay, which is in the other direction. So I'll just write e to the power I k a minus. Okay, and because I am doing this hopping, so I'll also write c k dagger c k. Okay, so now you see that without doing any of that complex algebra that we have done before, we've actually obtained the Hamiltonian for this single chain with one atom per unit cell. Okay, so this is just 2t cosine of ka ck dagger ck. Okay, so we have just obtained this result in two lines. Okay, without doing the whole thing. So this is kind of simple. So let me again repeat what I have done here. So first I will isolate what are the unit cells. Okay, I will just try to figure out what are the unit cells and where the hoppings are happening. So the hoppings are happening here, and there is also a conjugate process happening on the other direction. So whenever I have a hopping between two spatially separate places, so like I and I plus 1, these are actually spatially separated. So they are separated by distance a. Okay, so for that I'll write a e to the power I k a. Okay, so that means I'm I mean I'm making a hopping from one cell to another cell, okay, and I'll have Hermitian conjugate process, and you see that this actually gives us 2t cos k, okay. So I can generalize this process for the this SSH model as well, right? So for SSH model, this is a little bit complicated, so let's first try to identify what are the unit cells. So these are the unit cells, right? And there are hoppings happening between this intercell, and there are also hopping happening in the same unit cell, okay. So now as I have mentioned that this is I and this is I plus 1, and so let's write first this hopping term, okay. So this hopping term is actually given by V, so V, and you see there is no momentum exchange because it is happening in the same unit cell, okay. Whenever you have some processes happening in the same unit cell, you don't add any e to the power I k a, okay. So I have something like V and C K A dagger C K B, so I'll not write any e to the power I k, okay. So this just tells me that, okay, I mean the particle is going from A to B with momentum k, okay. And because the A and B are on the same unit cell, I will not add any e to the power I k, alright. So then the rest of the term is actually I am having a hopping between two unit cells we at position I and I plus 1. So I'll write W, okay, and then I'll write this C, let's say K A dagger C K B, okay. And because I have a hopping between I and I plus 1, so I'll write e to the power I k, okay. So you can write A as well. So if the distance, if these lengths are A, everything is separated by A, so you can write the e to the power I k. So that is your whole Hamiltonian, okay. And then you have a summation on k, and so you can just so there are also Hermitian conjugate parts, all right. So you can see that we have actually obtained the similar thing, exactly the same thing. V plus W sum e to the power I k B plus W e to the power minus I k, okay. So this is really cool technique to find out what are the dispersion, what are the Hamiltonian, just by eyeballing it, right? So this will, for 1D this might look very trivial, but for 2D I'm saying that this will save you a lot of work, okay. So let's very quickly let's talk about how you do the same trick for graphene, okay. So graphene, I think in assignment 2 you have to do some calculations using graphene. So yeah, so that assignment's due date is already done, so let me actually go ahead and tell you how do you do that. So I have some graphene here, so let me actually try to put it here. So and I don't need this many unit cells. Okay, so in graphene what I have is I have this this AB sublattice, right? So this is actually a triangular sublattice with this AB triangular lattice with a AB sublattice, okay. So something like that. So now, so the first task is, so you can again do the similar thing. You can write the real space Hamiltonian, and you can actually find out what is the you can do the Fourier transformation, and you can just figure it all out, right? But we are trying to eyeball it, right? So now you first thing is you identify what is a unit cell, okay. So unit cell you can choose in any way, but so my favorite choice is something like this. So the unit cell is given by just these two atoms, okay, two sublattice thing. So this is one unit cell and this is one unit cell, okay. So similar things you will have all over the place, right? So this is the unit cell that I have, and then I can see that there is actually some hoppings which are connecting between like this and this and this and this and this and this, and there is also hopping in the unit cell itself, okay. So let me annotate this by AB and AB, something like that. So okay, so so first of all, so after identifying what is the unit cell, okay, we can actually figure out what are the primitive vectors. So the primitive vectors here are given by these two vectors actually. Okay, so these are think it is lagging behind my screen. So let me try to reconnect. I think okay, something okay, so I think my okay, my iPad got disconnected, so let me actually connect it again. Yeah. Okay, so yeah, so then so the two primitive vectors are given by some vector a1 and a2. Okay, so this is the whole, I mean these are all the information that you need to write the Hamiltonian. Okay, so let me give you another piece of information, which is what are the hoppings. So like this hopping is let's say this is given by t1. Okay, so this hopping is given by t2 and this hopping is given by t3, something like that. Okay, I want to keep it general, very general. So in graphene actually all of this t1 is equal to t2 is equal to t3. Okay, but let me keep it very general. Okay, so that we understand what is actually happening under the hood. So now similarly I want to eyeball, right? I want to eyeball what is actually happening here. So I can see, so let me denote this one. I mean, what are the hoppings? 1, 2, or let me just write it directly. So between the single unit cell, I can see that there is a T1 hopping, right? So I'll directly write it as some T1 C K A dagger C K B. Okay, so you see that, so because A and B are in a single unit cell, so I actually don't need to add another e to the power I k. So like I mentioned previously, if these things belong in the same unit cell, you don't put any e to the power I k. But if they are separated and they are at different unit cells, then you put e to the power I k a properly. Okay, so this is one, this is T1. So T1 is just for this one. So we'll write Hermitian conjugate later, but I mean the Hermitian conjugate things are there. So then the second term, let's say the hopping, the T2 hopping also accompanies factors like this. So the T2 hopping actually goes from CK, let's say CKA dagger CKB, but now this has actually a exponential factor e to the power IKA. So now please just notice this. I mean what I have done here. So I mean I am seeing that okay, I have to go in this direction. Okay, so I'll put a e to the power I k, but in the a1 direction. Okay, so that is what this means. So you see that this is a T2 hopping. I have this creation and annihilation operators, but I have this important phase factor e to the power I k. Okay, so now you can guess what will come next. So for the T3 hopping, I'll have the same CK dagger CKB and e to the power I k dot a2. Okay, so because I am hopping in this direction. Okay, so I have e to the power ik2. So now you also add all the Hermitian conjugates. Okay, and there is a summation of k, so you get your Hamiltonian. Okay, so this is the most simple way you can obtain a tight binding Hamiltonian in the momentum space. Okay, where things are simple to calculate. So now if you write it in a matrix form, you will very soon notice that, I mean you recognize what is this thing. So T1 plus T2 e to the power I k dot a1 plus T3 e to the power I k a3, and this is Hermitian conjugate, and this is again 0. So this is your, let's say, matrix MK, and you can find the eigenvalues of this of this thing, right? And you are done. So so you're done with the graphene's thing. Okay, so now actually, so for graphene, so let's just mention this. So for graphene, so T1 is equal to T2 is equal to T3, and in that case you have actually Dirac cones sitting at some points like 4 pi by square root 3 a something like that, 1 0 plus minus 1 0. But so there are also another variations of this similar problem, where this T2 is same as T3, but which is not equal to T1. Okay, so then actually you get something different. So this is called a semi-Dirac model. So people have actually exhausted all of the possible combinations that you can have with this kind of Hamiltonian. So yeah, these are the things. So now you can see that there is 0 sitting at the diagonal. Now if you add some kind of electric field on top of this graphene, so electric field actually effectively enters in the diagonal part. So in the diagonal it will give you some coefficient, let's say some coefficients alpha and minus alpha. Okay, so when you will put something like that in the diagonal, you will see that the Dirac cone actually vanishes. Okay, so whenever so let's say this is the Dirac cone I had at some k and k prime point, so without alpha. As soon as I'll add some alpha, I'll see that this will actually gap out and become something like this. So the black lines are the dispersion when we have alpha, some electric field or something like that. Okay, so yeah, so this is all about tight binding models. So I hope you have get some practice of this kind of tight binding models, because if you're trying to do something some calculation, that this is the initial step. Okay, you first calculate the band structure, if I calculate what are the eigenvectors, because those are the things which will be used later on to calculate different things like linear response. Okay, or or many observables will depend on those eigenvectors and eigenvalues. Okay, or conductivity, something like that. So any questions so please feel free to ask. So I'd actually like to move on to the next topic. So I'd like to discuss some Feynman diagrams. Okay, so yeah, so I think Feynman diagram will appear later in your course, but I just because it is quite often it is appearing on your assignments. So I think it is kind of important so that you get some informal idea of what a Green's function is and how do you draw the diagrams. Okay, so I'll just show you in a way that this is like a jigsaw puzzle. Okay, you have some pieces and you just connect them to make a Green's function. Okay, so let's just talk about Feynman diagrams. Okay, so before Feynman, okay, so let me actually do it in this way. So Feynman diagrams has so what are the components when using Feynman diagrams? So these are something called Green's function, so which is denoted by some g, and if this Green's function is connecting between two let's say quantum numbers, then we write something like g beta alpha. Okay, so it is like so Green's function stands for when a particle is going from some quantum number alpha to some quantum number beta. Okay, so it don't have to be like quantum numbers, it can be positions, it can be some x to x prime, it can be xt to x prime t prime, something like that. So for all of these things, when one particle is changing its state from position to another position or from one quantum number to another, we can represent that this process with a Green's function. Okay, so Green's function is formally Green's function you can write. So for non-interacting case, when you have no interactions, no Coulomb interactions, no Howard interactions or anything like that, so then the Green's function is actually kind of easy to write. So let me write it g naught. So g naught means it is a non-interacting Green's function. So g naught at momentum k and omega is actually given by something like this, omega minus epsilon, and let me also give it the quantum number n k plus I delta. So this is called g naught retarded. Okay, so there are some variations of what kind of Green's function we have, so let's not get into that technicalities. But so this is what a Green's function is. Okay, so Green's function has all of the information that you are interested in. It has all of the information of what are the energy eigenstates. Okay, so everything like that. So because they actually appear at the as a pole in the Green's function. Okay, so this is a basic understanding of what a Green's function is. Okay, so we'll obviously dive into detail, but let's not bother too much about what is the exact form of the Green's function, because that will be not very much relevant right now. Okay, so one thing is you want to have the Green's function line. So this is one of the element to draw Feynman diagrams. And the second element is actually interaction. Okay, so let's say, I mean, we can have many kind of interaction, but in condensed matter physics, you are mostly interested in Coulomb interaction. Okay, there are also another interaction that you have in condensed matter physics, but for the Feynman diagrams, let's say we have just some Coulomb interactions. Okay, so Coulomb interaction is actually denoted by some wiggly line. Okay, so and then so these four lines are actually Green's functions, which are attached to the vertex. So now what does, so this Green's function also carry momentum, right? So the momentum, it will have k, and let's say this becomes k plus q, and this is some k prime, and this carries q, and this becomes k prime minus q. So let's just try to figure out what are the indices. So let's first look at this. So one of the electron is with momentum k is coming in. Okay, one electron with momentum k, and the electron with momentum k prime is actually coming in, and in between somewhere they're actually interacting through Coulomb interaction, and they're exchanging some momentum. So the exchange momentum is given by q. Okay, so they are coming together, exchanging momentum and going out, and so this one is actually taking k plus q, and this one is losing amount of momentum, so it is taking k prime minus q. Now you see that the way all of these indices are written, so that the incoming and outgoing momentum is exactly same, right? Because momentum is conserved when we have only Coulomb interaction. So incoming and outgoing momentum is actually conserved in that in the sense. So you also have frequency. I mean, each of the Green's function, as you see here, Green's particle has some energies, right? So the energies we often write with some omega. Okay, and it will also exchange energies and all. Okay, so it can also take some omega prime. So some q omega is coming from the Coulomb line, and it's left with omega minus let me write it as omega minus capital omega, omega plus capital omega. So you have all of these things. So energy and momentum are conserved. Okay, energy must have to be conserved, and momentum conservation is there if I have a periodic system, if I have some periodic boundary condition, and so on and so forth. So let me actually remove this, which is not important right now. So now let's say I have just these two things to draw all of the diagrams. Okay, so Feynman diagram is actually a perturbation series. Okay, so in a perturbation series in the Coulomb interaction. So let me write the Coulomb interaction as uq or vq. Okay, so Coulomb in some materials, Coulomb interaction is not that strong. So then sometimes you can actually write a expansion of Green's function in Coulomb interaction. Okay, so normally for non-interacting case you have only g naught. Okay, but as soon as you include interactions, now the interactions will try to change your Green's function. Okay, so now what will happen? So I have something like this Green's function. Initially I have some g naught. Okay, now I can actually plug in these vertices somehow. Okay, so I can plug in these vertices somehow in here. Okay, so that will give rise to all of the interacting Green's functions, right, in presence of interaction. So one way is to connect these two things. So let me just connect these two lines, so which is called a contraction, and then we can join these two lines. We can join this and this here and here. Okay, here and here. So let me actually draw that. And so okay, so you see that I just deformed it so that it looks quite somewhat better than this. Okay, so this is one of the diagram that I can generate. Okay, so now the whole game of Feynman diagram is like I have this Green's function and I have these vertices, and how can I actually combine them? Okay, and every possible combination is actually will give you some Green's function, some diagrams. Okay, so this is one of the Green's function, and then I can actually contract these two lines, right? So this line is contracted to this one. Okay, so that will actually give me another Feynman diagram, so which I can write something like in this way. So now you see that there are actually three Green's functions and one interaction line. Okay, and so what is the order of these diagrams? I mean, so we are trying to write a perturbation series, right? So we have to I mean, remind ourselves, so what is the order we are doing the calculations at. So this is actually order 1. So this is so this whole thing is order of UQ. Okay, because the interaction line appears only once. Okay, and so one important thing is, while constructing these Feynman diagrams, we have to remember that each of the vertices has to have two Green's function lines. One is incoming and another one is outgoing, and one Coulomb interaction line. So let's try to see whether this requirement is I mean, satisfied in this thing. Okay, otherwise it doesn't make sense, right? So because I cannot change this quantity, these are the elements. So like, just to make a simple analogy, so these are like all of your resistance and capacitor or LC, those things in a electrical circuit. Okay, so you cannot actually change them, you can combine them in various kind of way, right? So now look at this vertex. So this has one incoming line, another outgoing Green's function, and one Coulomb interaction. So that is actually okay. And this also has one outgoing and one incoming and one Coulomb interaction. So this is also okay. So this is also okay, and this is also okay. Okay, so this is everything that you can write at order 1. Okay, so as you write in the second order, you will see that things will become very difficult. So there will be many terms. Okay, and so one important thing is, whenever we'll write diagrams, so we'll only draw connected diagrams. So what are connected and what are disconnected? So let me first tell you what is a disconnected diagram. So for example, a disconnected diagram is something like this. Okay, so one electron is going through, and there is another electron which is actually doing something by itself. Okay, so this is called disconnected diagram. So you learn later that this disconnected diagram actually get cancelled. So this doesn't contribute in any way to Green's functions, okay, or to any observable quantities. So, and all of the other things where the electron line is actually connected with the rest of the things, so I mean, you cannot actually detach them, right? But here you can actually see that there is clear, I mean, you can separate it out. So these are actually examples of connected diagrams. So this is everything that you can write in first order, right? So you can try to do a little better, and you can try to see what I can put in the second order. So for example, I can put something like this, right? So you see, I have just taken one of this thing, I have made 2 copies of it, and this has 2 interaction lines. So this is a very well, I mean, it is a very good order of VQ square. Okay, so it will serve our purpose. So another thing that I can write is something like this. So I am just combining all of these things. Okay, so combining the whatever diagrams I had in the first order, so I can also have something like this. Okay, so here I have taken one of these and another of this, I have actually joined them. I can do something like this. Okay, so I mean, you have to draw arrows. I am not being that much careful, but you have to draw arrows, and you have to, when you are writing the expression of this Green's function, you have to make sure that each vertex, the energy and momentum is conserved, so that so that everything is consistent, everything physically makes sense. Okay, so you can actually do something more. So for example, a second order diagram can be something like this. So one interaction line and one interaction line, so they are crossing each other. Okay, so or you can have something like this, one interaction line goes like this and another interaction line is something like this, and so on and so forth. Okay, so there can be many combinations. Now we see that there are certainly some diagrams which are just by taking the first order and just like putting it in a GP series. Okay, so I'm just multiplying these diagrams things. So this twice comes from this diagram, so this and this, I'm taking this on this one and I've joined them, and this is just twice of this thing. Okay, so I mean, so there will be many diagrams obviously, okay, but right, but actually when you do any calculations, it is not possible to keep track of all of the diagrams, okay. So then it is important to identify a certain class of diagrams, right, and just to take them and just write all possible combinations of them. So what do I mean by that? So to see that, let's say on the order of VQ cube, so I can have diagram something like this, and I'll just put three of these things, okay. I can have two of these things and one of the other exchange kind of diagram, okay, and all sort of funny business that you can think of, okay, and so on and so forth. Okay, so there will be obviously many important diagrams which actually doesn't arise from just by first order, like this one, something like this, okay. This doesn't appear from the first order, so this will be something new in the third order, but you really cannot actually keep track of all of these diagrams, okay. So what we do in practice is just identify few diagrams, like let's say we are identifying just this two diagrams here, okay, and we will just make a GP series, okay. So just what do I mean by that? Let me actually write in a single line. So the Green's function is given by the 0th order, then the first order, which is given by this and this, and the second order is like a GP series of all of these things. And so on, and I'll just take these diagrams and I'll just stack them together, okay, and I'll just generate a new order, okay, and so on and so forth, okay. So I hope you are getting the idea that I am trying to what I'm trying to say here. So this way you can generate all of the diagrams, okay. So this is here, these two things are first order, these two things are, and there will be more, these are second order, and these things are third order, okay. So one interesting thing is, one important thing to note is, so this part is actually called the Hartree-Fock Green's function, okay. So so this is how you draw diagrams, right? So okay, so let me actually try to yeah, so now what I wanted to do next was, okay, so let's actually try to write a Green's function. So gk omega, so gk omega, so let's say my dispersion ek is just a quadratic dispersion, okay. It is nothing fancy, it is just h bar square k square by 2m, okay. It is just a parabolic dispersion, like a free electron, okay. So how do I write the Green's function for that? Okay, so the Green's function, this is not the interacting Green's function, this is just the bare Green's function. So this is given by 1 by omega minus epsilon k. So epsilon k here is h bar square k square by 2m plus a small convergence factor. So eta is a positive small number, okay, which is therefore convergence. So this is, this is how you write any of this Green's function. So for example, so today we have also seen that for a single for a 1D chain, the dispersion that you have is just minus 2t cos k. So you can also take this dispersion, right, and you can write the non-interacting Green's function for that. So what will happen? I'll just swap the energy with this one, okay. So that will give me the Green's function. So this is given by okay, so g naught k omega is given by 1 by omega minus twice of t cosine of k plus I eta, okay. And yeah, so this is what the yeah, so this is your Green's function. And for the other model of this SSH kind of model that we talked about, so the SSH model also, so now you have two bands, right? So you will have two Green's functions here for each of the bands. So each also, which will be given by, so g plus minus, so plus minus are for positive or negative band, and which are functions of momentum and omega. So this is given by something like this: 1 by omega minus v square plus w square plus 2v w cosine of k. So the dispersion relation that we calculated, so this will be plus minus plus eta. Okay, so you can just plug in the dispersion in here and you will get the non-interacting Green's functions. Okay, so let's actually try to derive once and only once to see why the Green's function has this kind of a symbolic form. Okay, so let's try to look at a very simple example. Okay, so let's say my Hamiltonian is actually given in terms of something like this: E alpha k, or just let's say E alpha, C alpha dagger, C alpha. So alpha is some quantum number. Okay, so alpha is some quantum number, and you can see that this is already given in a diagonal form. Okay, so so the Green's function is actually defined in, so Green's function for the alpha-th band, I mean our alpha-th level, which is a function of time, is given by something like this: theta t and expectation value of c t dagger c 0. Okay, or the other way around. Yeah, dagger is on this. So this means that I am actually creating a particle at time 0 at the alpha-th level, and I am letting it propagate for some time t, and then I am trying to measuring, okay, what is the amplitude. Okay, so this is, I mean, normal form, I mean a general form of any Green's function that you will find in condensed matter physics, or in also in high energy physics. So this is the same Green's function that they talk about. So, and you might also remember from your quantum mechanics, or I mean, so the time dependence of this thing, I mean, you can find out from the Heisenberg's equation of motion. So which turns out to be something like this: e to the power minus I epsilon alpha t c alpha. So c alpha 0, I am just denoting it by c alpha without any braces, parentheses and all. Okay, so if I just plug it in here, so what do I get? And so this expectation value, I mean this is the expectation value. This definition of expectation value might differ depending on I mean what is you are trying to do. So it can be on a thermodynamic ensemble, it can be on the ground state. Okay, so you have to, I mean, if you are reading some literature, you have to try to understand the context on which this calculation is happening. Okay, so it can be thermodynamic ensemble, it can be ground state, or it can be on any different kind of density matrix. Okay, so anyway, so that is something technical. So I'll just plug this thing in. So theta of t, right, and so c alpha t gives me 1 by e to the minus e alpha t c alpha dagger. Okay, so you can actually see from here. So c alpha dagger, c alpha, this expectation value is actually given by in the Fermi function 1 by, or let me write it as Fermi function e alpha. Okay, so which is given by 1 by e to the power beta epsilon alpha, okay, plus 1. So this is the occupation of the alpha-th band. Okay, so yeah, so you can so you will just write this as 1 minus nf, or if, so, or let me write it just f alpha. Okay, and then there is theta t e to the power minus I epsilon alpha t. Okay, so now so it is useful to go to the omega space, or the frequency space, where things becomes very simple. Okay, and even simpler than this. So to go to momentum, to go to frequency space, what we do is we just do these Fourier transformations, right? So g omega, so I, let's say I g alpha omega is given by e to the power I omega t theta of t e to the power minus I epsilon alpha t and c alpha. Okay, so actually, yeah. So okay, so the definition of retarded is I mean, that is given by a commutator. Okay, so I actually did this mistake. So this is a commutator. Yeah. Okay, so it is not then so much easy to write it, but then okay. Okay. So these are fermions. So these are actually anti-commutators. So these are anti-commutators. Okay, and then the anti-commutator is just one, right? So I mean, it actually just goes away. So there is nothing else in here. So I mean, we don't need to introduce the occupation numbers and all. So and the integration goes from minus infinity to infinity, and the integration is over the time. Okay, so so you see that the theta t is a heaviside theta function. So the function actually looks something like this. So this is, let's say, your t is equal to 0, and the heaviside theta function is 0 until t0, but it actually goes to 1 when the argument is greater than 0, right? So that actually restricts the Hamiltonian or restricts the integration from 0 to infinity. So and we have minus e to the power I epsilon alpha t. Okay, so now there is a trick that people use. So I mean, you can see that we just have exponential factors, and at infinity I mean, so this is not actually a well defined thing, right? So what people do is they will add some convergence factor, okay, to make it converge. So I will add something like omega eta t, okay, omega I e to the power I eta t. So eta is a very small positive number, okay. So you can see that when t goes to infinity, okay, and then I will have something like e to the power I, and eta is very small, and okay, so I actually, yeah, I should actually write it not in this way but in this way, e to the power minus eta t, let's say. Okay, so you can see that when t goes to infinity, this factor actually makes the integral 0. Okay, so this becomes a bounded integral, this becomes a well defined integral. Okay, so let's arrange these things in a little I mean, in a better way, and try to do this integration. I omega minus e alpha plus I eta t, right? So this is a simple integration, and you already know what the result is. So just let me write down, and on top we have just exponential minus sun alpha plus I eta t, and the limits goes from 0 to infinity. Okay, so at infinity I already know that this is 0 because of the convergence factor, but at 0 this will give me minus 1 by I omega minus epsilon alpha plus I eta. Okay, so this is everything that I wanted to have. So this is g alpha at omega, which is given by I 1 by omega minus epsilon alpha plus I eta. Okay, so I can remove the I from both of the sides, and this is the Green's function, right? So I mean you see, if you are given a Hamiltonian which is given in a diagonal form like E alpha, C alpha dagger, C alpha, so then the Green's function for that is always, the non-interacting Green's function is always this. Okay, so I mean you can also think about, so you have some Hamiltonian, okay, so you have some block Hamiltonian, right? So you can also take that and you can just plug in, I mean your alpha becomes momentum, block momentum, and you can do the similar business. You will be able to find out what is the Green's function for this non-interacting Green's functions for this Hamiltonian. Okay, so as simple as that. So any other quantum number you have, you just take that Hamilton in the diagonal form, and you just plug in back in this expression of Green's function. Okay, so now one subtlety is what happens if your Hamiltonian is not in a diagonal form. For example, so let's say your Hamiltonian is something by minus t I c I dagger c I plus 1, okay, something like this. And what you do, so first thing is you always try to reduce this in a diagonal, so diagonal form. So in a diagonal form it becomes some en cn dagger cn. So let's say n is the index of levels or something like that. So the first thing is, if your Hamilton is not in a diagonal form, you diagonalize it, and from the diagonal values, those eigenvalues of the Hamilton, you plug in back in your Green's function. Okay, and the Green's function will take the index of the energy levels, which might be energy levels or might be momentum. Okay, so that is the way to go. So yeah, so this is how any kind of a non-interacting Green's function looks like. All right, so yeah, so so there is another thing that I want to talk about, Feynman diagrams. So like I said that you can have like stack the Feynman diagrams together to make a new order, right? So for example, so I am again reiterating myself, so I can have some diagrams like this, or I can have the diagrams like this. Okay, and you can see that this is kind of a GP series, and 3 of these tadpoles, and goes on and on. Okay, so we see that if we take this, let's say this part common, so if I just take this part common, then the rest of the term is actually common for all of these things. So on and so forth. Okay, so this is what I am writing, the interacting Green's function, right? So the interacting Green's function has this kind of a diagrammatic representation. So now you see that, so there is a recursive kind of structure which is appearing in this thing. So this is a GP series. This is called the Dyson equation. Okay, so the Dyson equation is in real space, it is a integral equation to find the interacting Green's function. In momentum space, although, it becomes an algebraic equation. Okay, so this is called a Dyson equation, and you can see that if I am calling this whole thing as G, if the whole thing is called a G, then this thing is also a G, right? So let me actually write it in this way. So G is given by some G naught plus some G naught times some sigma. So I am calling this thing as my sigma. So I have this thing which is called as G naught. Okay, and this tadpole kind of thing, which is called, this is called really a tadpole diagram. So this tadpole diagram is my sigma. Okay, and then I am left with the G, right? So this is the G. So now you see that this is actually a recursive kind of expression. So G is written in terms of G. Okay, so now how do you solve it? So if these are if these are like electron free electrons which are just k square by k square dispersion, then you can actually take these things, you can simplify these things a lot. So G minus G naught sigma G is given by G naught. So you see what I have done here is, I have taken this piece and I brought it back on the left hand side. Okay, so now I can actually take these things common. So let me write is identity minus G naught sigma, and I am taking G common and G naught. Okay, and then the G is actually given by something like this, identity minus G naught sigma inverse G naught. So I have taken this thing, I inverted it to here. Okay, so now if your Green's function doesn't have any dimension, or this is just a function, then it is just like something like this, G naught 1 minus G naught sigma. Okay, and you can actually see that this is the formula of a GP series. Okay, this is how you sum a infinite geometric progressive series. Okay, so this is how the interacting Green's function can be obtained. Okay, so yeah, this is one point that I wanted to make about these Green's functions. So yeah, so I'm done. Whatever I want to talk about Feynman diagrams and Green's function, I'm done with that. So the last thing that I want to discuss about today is actually some Hubbard model. Okay, So let's actually dig in. Yeah. Alright, so you already learned some amount of Hubbard model. So let me recap what a Hubbard model is. So Hubbard model, the Hamiltonian of Hubbard model is given by this expression. So it has some electrons which is hopping. So let me write it as Cj sigma dagger Cj sigma. So there is a sum over okay, so let me write it as Inj. Inj can be nearest neighbors and all, and sigma is the spin. So electrons with spins are hopping. Okay, so this is the kinetic part of the Hubbard model, and then there is the interaction part of Hubbard model, which is given by something like this. Down, right? So this is on-site Coulomb interaction. Okay, so what happens is in some materials Coulomb interaction is screened. So beyond, I mean, on the next side, the Coulomb, I mean, the particles cannot even feel the Coulomb interaction. Okay, so this is some approximation because the exact problem is, I mean, difficult to solve. Okay, so there are only approximate solutions. So we are approximating that the Coulomb interaction is only working on each of the sides. Okay, so if you trying to put two electrons on the same side, then you have an additional cost of u. Okay, which is the Coulomb interactions magnitude, and then you have the chemical potential on site, right? So which is given by Ni sigma. So Ni sigma is the summation. Okay, so no, this is okay. So this is the Hubbard Hamiltonian that you know of, but the exactly same Hamiltonian can be casted in a different form, right? So it can be written in a slightly different way, so that it will have particle hole symmetry. Okay, so particle hole symmetry means that if I have some energy of an electron, then the hole will have the exactly opposite kind of energy. Okay, so that symmetry is there when we cast the Hubbard Hamiltonian in a slightly different way. Okay, but I mean, which is the same. We'll be adding just constant terms, which actually doesn't do anything to the eigenvalues. It just shifts them. So we don't bother about adding some. We don't find it wrong to add some constants, right? So let me write it in a different form. So let's say cast it. So let me write it in the form. So I'll not change the kinetic part. J sigma, and so I'll just change the interaction part. So which is given by Ni up minus half, and Ni down minus half, minus mu I sigma NIS. Okay, Ni sigma. So you see that this is the I mean, these are some things that I have added. Okay, but I mean, if you open up the bracket and you try to simplify, you will see that I have just added some constant terms. Okay, so it actually doesn't change any physics that we are concerned about. So so now this Hamiltonian in this form has something called a particle hole symmetry. Okay, so normally one sec. Yeah, so yeah, so this is the Hamiltonian, right? So so we'll be using this Hamiltonian to do some calculations and all. So now you can actually okay, so what do I mean by particle hole symmetry? So the particle hole symmetry is actually defined by this kind of transformation. So let's say I am changing all of this fermion operator C to be something like this, minus 1 to the power I Ci sigma. So all of the C's are actually changed to D, some with a minus sign. Depending on if I am on some even side, I'll put a plus 1. If I am on odd side, I'll put a minus 1. and also you can also the daggers also are defined in a similar way. Okay, so you see that if you just do this transformation, you see that your Hamiltonian actually doesn't change. Okay, so this is the particle hole operation that you do, and you see that doesn't change the Hamiltonian. So you call it the Hamiltonian is actually particle hole symmetry. Okay, so okay, so with that, so let's talk about what is the dimensionality of the Hilbert space. So we will remind ourselves now, if we have a single site. Okay, you have a single site, and I mean we can put one spin, we can put spin up, we can put spin down, we can put spin up and spin down, and also we can also put nothing, right? So these are all the possibilities that we can think about. So what is the Hilbert space on if I have a single site? So let me write it like this. So I have zero particle, I can have zero particle. Okay, I can have one up spin, I can have one down spin, I can have up and down. So this is the double occupancy. Okay, so I cannot have anything like up because I have only one site, and Pauli exclusion actually does not allows us to put anything like that. So our single site, in a single site, the Hilbert space has dimension 4. Okay, so and then similarly, if I want to write the Hamiltonian in this dimension, it has to be a 4x4 Hamiltonian, right? So now if I add another identical site to our already single site, then it also comes with its four similar basis vectors for the Hilbert space, right? So as you add on more and more, so if you have added n particles, so for n particles, for let's say n sites, this is the dimension of Hilbert space. So I am writing is with some calligraphic h. So dimension is actually n to the power 4. Okay, so dimension, as you add one by one the spins, the dimension actually grows exponentially. Okay, so just to give you a number, how does it grow? So normally when you have such a huge Hamiltonian, you can never think about solving it analytically. Okay, we have to put it in a computer, but there is a limit to which a computer can actually solve things. Okay, so I'll just to so that you appreciate it in more, I'll just show you what are the numbers. I mean, how large system you can fit in a typical computer's RAM, typical computer's memory. So for example, let's say you have 10 sites. Okay, and each site comes with a four-dimensional Hilbert space. Okay, so our Hilbert space dimension is 10 to the power 4. Okay, or let me write it as 10 to the power 4. Okay, and normally these are complex entries. Okay, these are complex numbers. So the complex number actually takes 16 byte. Okay, so this is the if you are just talking about your basis vector, so this is the size of a single basis vector, n to the power 4 times 16 byte. Okay, so I'm talking about memory now. So these are n to the power 4 by 16 byte. Now I want to write a Hamiltonian in this whole basis. So then the dimension actually becomes actually square of it, right? Because my matrix Hamiltonian is a square matrix, so it becomes n to the power 4 times 16 square. So dimension of a matrix of Hamiltonian. Right, so just to give you some numbers, so these are in the byte, right? And 1 gigabyte means 10 to the power 9 byte. So now if you just take this whole thing in square, n to the power 4 into 16 square by 10 to the power 9, so you will get the answer in gigabyte. Okay, so if n is like 10, so then this will give you something like 26 gigabyte. Okay, So normally a computer, I mean a personal computer has RAM, let's say 8 gigabyte, 16 gigabyte. But you see that only I have 10 number of sites in the Hubbard model. So, but the memory I require to save the Hamiltonian, okay, is already exceeding, it's already about 26 gigabytes, right? So in normal typical personal computer, I cannot do this numerical things, okay. So I have to use some supercomputer, some computing facilities, right? But still also there is a bound, okay. You cannot actually go beyond, I mean, let's say 20 or 30 spins, okay, in a single, so normally a particle, I mean if you talk about matter, in any metal or any object that you take, it has Avogadro number of things, right? Avogadro number of particles. But I mean you can see that it is, I mean we can already only solve of the order of 10s and 20s of sites in the Hubbard model, okay. So and this is still active research, but I mean because so you can have some terabytes of RAM, okay, but still you will not be able to fit inside some, let's say 50 spins in that terabytes of RAM, okay. So this is some I mean really some restriction on classical computers. But so when quantum computers will be like really available to researchers, I mean in a large scale, then probably they can actually scale that up, okay, because I mean that will give you some exponential exponentially exponentially reduce your number of operations that you have to do. And so this is just to give you some numbers so that you can appreciate that this is actually impossible to do by analytical techniques, right? But even after saying that, so there are some limits that you can solve the Hubbard model exactly, okay. So which are two limits when your u by t, so u is the interaction and t is the this hopping term, is very small, okay, very small, or u by t is actually very large, okay. So this is called a strong coupling regime, okay, and this is this is called a weak coupling. So then you can actually do a perturbation series in u by t, okay, and here you can do a perturbation series in t by u. So we'll look into some examples probably next week, okay. So you can do perturbation series in different orders, but in between, so if this is finite, okay, so let's say if u by t is finite, so there is no analytical techniques to give you an exact answer, okay. So there are approximate techniques which are also numerical. So approximate techniques, I'll just mention few. So one of which is very famous, which is called quantum Monte Carlo. So there is another algorithm called DMRG. Yeah, so it stands for density matrix. Denormalization group. Okay, and along there can be something also. So this is just to mention few. And the exact thing that you can do, so which I already mentioned. So you take a huge matrix which is like gigabytes of size, okay, and you can plug into some linear algebra system, and you can find the exact eigenvalues, or you can at least find a ground state, which is actually quite enough for to calculate the zero temperature or low temperature properties, right? So that will give you an exact answer if you can fit that in your RAM, okay. So this is called exact diagonalization. So this is also numerical. This is also a numerical thing, but this is the exact thing that you will have. Okay. So if you have any results through any other process, if it doesn't come any closer to exact diagonalization, then that means that your result is just not. It is not just doing the correct. It is not predicting the correct physics. Okay. So yeah, so just to give you, I mean, what is, I mean, and these are actually forefront of research. So in people in statistical mechanics, they take these huge models and they do some of these things. Okay, so these are actually very active topics in research. So they will have some Ising model, some XY model, and they will calculate something. They will add they can do Fourier transformation, and they can calculate localization physics. So many things. Okay, so yeah, so these are just to give you some update about what, I mean, what are the current I mean, important things going on in using this kind of spin models. Okay, so with all of these things, let us actually be somewhat less I mean ambitious, and let us actually first look at a single site Hubbard model. Okay, so in a single site Hubbard, so that means that I have a single site. Okay, so I can put one spin here, or I can put let's say two spin here, or I can also not put anything. Okay, so my Hilbert space is actually of dimension 4. Okay, so then so in this thing I like to solve the Hubbard model. Okay, so and I'll show you that it has an exact solution, because the dimension is already 4 and you can find the eigenvalues really very simply. So I'll show you how to find the eigenvalues of these things. Okay, so now so it is worth mentioning that if I have only one site, so electrons cannot hop to any other site because there is no another site left, right? So there is no hopping term in the Hamiltonian, but so there are only interaction terms and the and chemical potential, right? So all those things will be there. So let me denote my single site Hubbard model as H1. Okay, so this is given by U in up. So I'm not writing any site index because I have only one site. So in up minus half, in down minus half, minus mu in up plus in down. Okay, so this is my whole Hamiltonian. I don't have anything else, right? So
Excuse me.
yeah,
If there is only one site, then what is the interaction between
yeah,
with-
yeah. Okay, so yeah, thanks
there
for
is no hopping. There is no hopping,
yeah,
right?
yeah.
It's fine. But interaction with which particle?
Right.
If
Yeah,
there
so
is one site.
that's a good question. So let's say I have only one site. Okay, so if I am one site, so Howard interaction that you have already studied is actually interaction between a spin up and spin down in a single site. Okay, so if I put only one spin, then there is no interaction really. Okay,
Yeah.
so then I mean the interaction, so you in up, you in okay, so in down will be 0 for this. If I have just only one term, only one spin, but if I put two spin, then actually that will give me something non-zero. Okay, so this
Yeah.
term will be non-zero.
Okay.
So the interaction is actually on the single site, on the same site. So that's why I was talking about if I have only one single site, I do not
Yeah.
have any hopping, but I have
Yeah.
interaction on the same site. Okay, so that is Howard interaction about. So you can, so the thing that you're talking about is actually somewhat I mean some generalized version of the Hubbard model. So you can actually talk about some ni and ni plus 1, some sigma. So you can write an interaction something like this, so that it actually the interaction is between I and I plus 1. Okay, so yeah, something like that, but we are not actually talking about that thing yet, but we're talking about the simplest Hubbard model that you can think about, which is just a single site Hubbard model. Okay, so there is no hopping and there is only interaction.
Oh,
yeah,
thank you.
yeah. So now what we are trying to do is so we know what are the bases, right? So the basis consists of these 4 states: up, down, and double occupancy, up down. Okay, so we can actually write a second quantized version, I mean in terms of creation annihilation operators. So just let me write this, so that, so 0 is just 0. 0 is a vacuum, there is nothing. So up spin means that I can actually create one up on this vacuum, and I am not writing any site index because there is none, there is only single. So I can write okay, so this is dagger, I can write C down dagger acting on 0. right? So that will give me a down spin. So I can write something like this: C up dagger, C down dagger acting on this vacuum. Okay, so these are all of the bases that I can have. Okay, so because these are the basis of my Hilbert space, so any operator that I'll form, like the Hamiltonian, will have to be expanded into this Hilbert space. Okay, so let's first try to find the matrix elements of this H1. Okay, so yeah, so before that, so if I mean, let me just show you how does this n actually acts on these states. So if n acts on 0, so let's say so this will give me 0, right? So if n acts on, let's say, sigma, so n actually counts what are the number of up spins on this side. So it will give me actually just 1 times that same vector. Okay, so if I act n on the down spin, then that will give me actually 0, because there is no up spin on that thing. If I act n on this double occupancy state, it will give me 1 up down, because in the double occupancy there is one which is one spin, which is up spin. Okay, so you can do the similar business for all of the others, all of the n down also. Okay, so yeah, so let me actually try to find the matrix elements of this H1. Okay, so let me simplify the Hamiltonian a little bit, so that action on the states become a little easier. So I am just expanding out the parenthesis. Okay, so u n up n down minus u by 2 n up plus n down plus u by 4. So this is coming from the parenthesis, minus minus mu n up plus n down. Okay, so I can simplify, I can do one more simplification, minus I can actually combine this u and mu together, e by 2 plus mu n up plus n down plus u by 4. So this is my H1. Okay, so now this is my Hamiltonian. Now let's act this Hamiltonian on the vacuum state. Okay, so that means on the vacuum there is nothing, there is no spins. So if I act that, then so let me just write all of these things so that it becomes absolutely clear what I'm trying to achieve. E by 2 plus mu n up plus n down acting on 0 plus u by 4 acting on 0. Okay, so now when this so this thing will hit this, so I mean this state actually doesn't have any up or down, right? So this both of these operators will act on this state, this will just generate 0. So 0 for this particular state. And similarly, whenever this will act on this, so this will also give me a 0, and this will also give me a 0, because there is not even a single up or down spins, right? So the first two terms actually goes away. So now what I am left with is I am left with just H1 acting on 0 will give me u by 4 0. Okay, so now I see that, okay, so 0 is actually its eigenstate, right? So so that means I can have only this matrix element non-zero with this 0, so u by 4. So this is one of the matrix element. Okay, so I find every matrix element with zeros, with vacuum states. There is no other vacuum matrix element. So now let's act this H1 on, let's say, spin up. Okay, so similarly we'll just act all our I mean term by term on this state is up state. So n down up minus u by 2 plus mu, and then n up plus n down 0. Okay, not 0 actually, so and plus u by 4 and up. Okay, so now here I can see that so when this thing up, when down will act on this one, so because there is no down spin, so that will give me a 0, right? But when this will act on this one, so that will give me 1, but I am already getting a 0. So 0 times 1 is 0. So this thing actually will go away. This will become 0. So now if I act this n down on this thing, because it is just a single up spin, so there is no down spin, so this will give me 0, and this will give me actually plus 1. Okay, this will give me 1. So I mean, not all of this thing is 0. So now I can write this whole thing, right? So the whole thing, if I just put it together, this becomes u by 2 by plus mu plus u by 4. Is that plus u by 4? Yeah, plus u by 4, everything acting on spin up. Okay, so you can see that this is actually minus u by 4 minus mu acting on, and I mean, by coincidence we are seeing that okay, this is also actually an eigenstate, right? So we actually found a diagonal element of the Hamiltonian. So that means that upspin h1 upspin, this thing will give me just minus u by 4 minus mu, right? So we have find another element of this matrix. So actually you will see that I mean, so let me just give you a spoiler. So you will see that all of these 4 bases that I talked about, that spans the basis of a single single site Hubbard model. So both of these are actually eigenstates of the Hamiltonian. Okay, so we have just to find the eigenvalues by acting it on top of each other. Okay, so when you understand that the n's actually count the number of each of this number of spins, then it becomes really easy. Okay, it becomes intuitive and kind of easy. So if you just calculate h or acting on down, so you will see that you will get the exactly same result. You will get u by 4 minus mu. So you can check that. Okay, and so the last thing that we'd like to calculate is h acting on this double occupancy state. Okay, so this let's just do this. So I have this u operator, u element n up, n down, acting on this up and down, and then minus u by 2 plus mu with n up plus n down acting on this up and down. Okay, and plus u by 4 acting on this up and down. Okay, so now I mean, interestingly we see that because you see whenever, so Coulomb interaction is only there when there are 2 particles. Okay, so you see that, so this is the only term actually, I mean, this actually contributes for this one. Why is that? Because when n up n down acts on this one, this gives you plus 1, this gives you 1, and n up acts on this state, it also gives you 1. So 1 times 1, right? So this whole thing is actually 1. So I'll just write it u up down. Okay, so for the first term. So in the second term we see that so this will give you 1 because I have 1 down spin, and this, when I will act on this one, this will give me 1 because I have 1 up spin as well in this double occupancy state. So then for that I will actually write u by 2 plus mu. So this will give me 2 up down. So 1 plus 1 2 up down, and then I will be left with u by 4 up and down. So that is a number, so that doesn't do anything to this state. So this is, again, you see that this is an eigenstate, right? H acting on this state doesn't change it. So it gives you some number times that state, so it is an eigenstate. So let me actually combine all of these things together, and let me not make any silly mistake. So u minus 2 mu plus u by 4. Yeah, so up down is this. Yeah, so you see this cancels, and you are left with u by 4 minus 2 mu up and down. So this is, again, I mean, this will give you the matrix element only up down, u by 4 minus 2 mu, right? So see, so I mean, we actually know all of these eigenvalues, right? So what are the eigenvalues? So the states are 0, up, down, and this double occupancy, right? So so for the double occupancy, at least we know that this is u by 4 minus 2 mu, right? And then for 0 we know it is actually just u by 4, and for this rest of these two things, this is u by 4 minus mu minus u by 4 minus mu. So we see that these two single up and single spin, these are actually degenerate. Okay, so this is the whole solution of the single site Hubbard model. Okay, so now if you know this thing, now you can actually construct the full statistical mechanics of it. So you can write the partition function, right? So the partition function is given by z is equal to trace of e to the power minus beta h. Okay, so you can take this, so the trace is again on this same Hilbert space. Okay, so I mean, which is just so let me write it properly. 0 e to the minus beta h, 0 plus up e to the power minus beta h, up plus down e to the power minus beta h, down plus up down e to the power minus beta h, up and down. Okay, so now because these are already the eigenstates, so you can actually just very simply calculate it. So the first term will give you e to the power minus beta u by 4. Second time will give second and third term will give you, I mean these are same energy, so you can directly write it minus beta minus u by 4 minus mu, and then the third term will give you e to the power minus beta u by 4 minus 2 mu. Okay, so as soon as you know the partition function, so you can calculate a lot of things. Okay, so you can actually calculate what is the occupation. So occupation is given by the expectation value of a, or the average thermal average of n up and n down. Okay, so this also has some interesting features. Okay, and so probably so I'll show you how to calculate some interesting stuff out of this this Hubbard model. Okay, so next time I'll show you some calculations, or next time I'll show you also how do you calculate using the same machinery, I mean, which is actually very simple. Okay, so same machinery, how to calculate Green's functions of this Hubbard model. So we'll also see how do you how can you get exact solution for two-site Hubbard models. Okay, so for two-site Hubbard model, we'll have hoppings, additional hopping, which we are not considering for a single site. So yeah, so the for two site the things are still, you can still do everything by hand, but as it grows like 3-4, things will be very difficult. The Hilbert space size will become very large, and it will be very hard to keep track of everything. Okay, so then you'll have to get the help of a computer. Okay, so I mean, so I'll just leave you with this thought that you can get the energies, exact eigenstates and eigenvalues of a single site Hubbard model, and you can find the partition function, the canonical partition function, and you can find like all thermodynamic quantity that you like for this kind of a system, right? So I mean, I'll talk more on this probably next time. We are already more than 2 hours probably. Yeah, you might be getting tired, and so I mean, so am I. So yeah, so any questions, so you can ask me. So yeah, so Payal, you are just the one who actually attended the whole class. Yeah. Thank you for that. Yeah. So yeah.
Thank you for your efforts.
Yeah. So yeah. So I it seems like neither do you and I have interesting things to do in the weekend. so yeah, we're talking about physics. Yeah, but that's good. So yeah, I mean, if you have any questions, you can actually post on this Google thing. So which I saw that no one was actually maintaining it. So I actually saw it yesterday. So there are many questions which are not answered. But yeah, I'll try to make sure that those questions are answered. I'll talk to other TAs and try to make sure those are answered. But yeah, so these are
This class was really constructive.
Oh yeah, yeah. Actually, 2 hours is actually, it is very hard to keep your focus. But I mean, yeah, it's so thanks
for
if you
both,
get
like
something.
for you also talking for 2 hours constantly is
Yeah, it's
a
very
bit
tiring.
tough.
But I mean, it's all worth it if you learn something out of this.
Yeah.
Yeah.
No. Yeah.
So
Really, I enjoyed this class today.
okay. So Payal, where you are from?
I'm basically from Assam, and now I'm staying in Kolkata.
Okay. So and you are at which college?
Actually, I'm doing my PhD from Institute of Engineering and Management.
Oh, I see. Okay. So I stayed at
So,
Kolkata for 3 years. So I was I did my BSc from Scottish Church College.
okay. I did
So
my BSc from this one, Cotton College, Guwahati,
I see.
and
I
yeah,
see. I
and
see.
masters from Guwahati University.
I see. Okay. So yeah. So yeah. So yeah. Nice to have you.
Yeah.
So yeah, and so one thing that I like to
So, can I ask one thing?
yeah.
So you were working in this field only, like theoretical condensed matter.
So yeah, I am working in this theoretical condensed matter physics, but not so much on this Hubbard model. So the Hubbard
Oh,
model is
yeah,
really
that's different. Like research, and I can understand. There's
yeah.
a
So yeah, so I'm so theoretical. Yeah, mostly we do this theoretical condensed matter physics. So some mesoscopic physics, like we calculate many body quantities like transport, conductivity.
oh
We do
oh
flocke and all sort of this kind of stuff.
oh.
So yeah, this is kind of a little bit home ground for me. But the
I'm
how
yeah.
yeah. So go on.
Okay, I'm working on spintronics.
Oh, spintronics. Oh, it's
Yeah,
nice. Okay.
yeah.
Okay, so oh, I see. Okay, that's very nice. So yeah, so I just want to just give you with one link. So the video of this thing will be so this will be uploaded in YouTube, but I think you are not getting the
Oh,
links of that thing.
yeah, yeah.
And this note will also be uploaded so that you can later on look into it. If you find some mistakes, you can also tell me about it. So let me
Video
actually.
I didn't find, and like I was also doing with you, so
Oh yeah.
I think it's
So yeah. In any case, so I'll just give you the link. So let me actually just copy paste in the chat. Yeah.
sure.
So I don't know. I mean, I also could not find from the NPTEL's course website. So I'll just give you in this link. So okay, where is the chat? Yeah. So just keep this link handy so that yeah, probably you can so you can look at some point of time. Okay, so it will be uploaded in that thing. So all of the videos links are there. All of the these notes are there. Okay.
Mm-hmm.
And yeah, so I mean, I think it will be helpful.
Oh,
Okay, so so I think yeah, so it's probably time. So yeah, I'll see you I think in the next week. Okay,
yeah, sure.
so yeah, have fun for the rest of your weekend, and I will also try to have some fun.
Yeah.
Okay, yeah, okay. Thank you for
Oh,
joining in.
oh,
Okay.
bye. Yeah.